Welcome to the second part of Online Academy. Today, the topic is horizontal milling of grooves, faceplates, and lockpockets. Today, we will focus on the machining principles for those kinds of machinings, and we will start with milling of grooves. Therefore, we prepared the different parts with different grooves on it and the machining principles. Let's switch to the organizer. And take a look on our machining principles. We extended our folder structure here. Now it's Online Academy, mill, grooves, and horizontal. And we will start with a milling of grooves. So our first machining principle is for the milling of grooves, and what is important, the machining type should be slot milling horizontal. The machining class is again Woodwop 7 and our machine from our workflow from the last Online Academies. In this Online Academy, I will not explain the conditions very detailed because it was explained already for the previous one. Online Academy, we will focus on the machining properties of the tools. We can see our tool here again. It's a mill number 108 from the Woodwop database with a diameter of 8 millimeters. And we can see here our basic settings again. The first very important setting is output of the pocket. It is VOP macro in this case, but it could also be center contour train because the slots, the grooves, is nothing else than the pockets. And the same principle is also working here, VOP macro or center contour train 1. There is one option more, center contour train 2 without correction. It will be explained on the next Online Academy, and on this Online Academy we will work with VOP macro and center contour train 1 for the lock pockets. In feed in percent. In the previous Online Academy we wrote here the tap function. In this case it makes not so much sense to write the tap function here, but it's still possible. Now here is a fixed value for the in-feed in percent, for the adjustment in percent, 80%. In the contour settings, we can see again the feed depth with the tap function from the previous Online Academy. And what we see now here, the new settings, is prolong the contour at the start and prolong the contour at the end. And here are the values, the fixed values in millimeters. It means if the values are written here, the contour, the rabbet will be extended on the start and on the end point to 50 millimeters from each side. And we can also set here a condition. For example, only execute extension if distance to outer contour is less than 0. It means if the groove is going from the edge to the edge. In all other cases, it should not be active. We have here some more settings in feed via center. We will use it today as well when we will switch to center contour train 1. And the settings split groove in length and merge grooves. Those two options we will explain on the next Online Academy on the 5th of January. Will come the Online Academy for the grooves and for the vertical grooves, and it's better to show these functions for the vertical grooves. Split groove and merge groove. The fixed depth We know already what it is in the previous online academy. So let's generate the first program and switch to CAD. The first part here has a groove with width 10, and it starts in X at 50 here and ends in X at 750. It means it's not going through the whole length. And let's generate the program and see the result. So we will open it in Woodwork 7, and what we have groove with the mill in Y+. It's correct, it's a macro. Now with the double point we can see which tool is here, and the step depth comes from our tab function, and the adjustment in percent is 80. That's correct. And what we also can see here, this function prolong at the contour at start at the end is not active, because it should be only done if the distance to the outer contour is less than 0. This example we have prepared also. I switch to the next part and switch the editing. And the groove here, we can see here, it's already on the part that's from the edge to the edge, from 0 to 800 through the whole length, the same width and the same depth. So I will select the part and create the CNC data. And now I can see those extensions, 50 from the start and 50 from the end, because there is no distance to the outer contour, means to the outer sides of this part. With the same tool, the adjustment and the step depth is also performed. It is working correct. But usually it might happen then you don't have this option on your machine to mill horizontal, and on some machines are the tools, the saw, which is in fact the mill in the machine. For example, it could be this kind of tool. It's a mill, and it's saw as a mill, saw prepared as a mill, because there is no option to on the machine to make it, no possibility. Oops. It is no possibility to make it with a standard mill like that. Yeah, it should be sawed with a mill, so to say. It is also possible here. For example, we can take this kind of saw as a mill and create it in the database of the tools of IMOS. Here is our slot miller. It is done like a saw here. You can see here IX saw. The number is 181, and the cutting width is 3 millimeters, 3.67 millimeters, and the other options. So to mill with the saw, we have to create an additional machining principle for our slot miller. Now it is machining type not mill anymore, but the saw, and the machining type is groove sawing horizontal. And as a comment I wrote saw as mill. I also can see here the tool. That's my slot miller, my mill, which has also the saw blade. And the following settings below are important now. First of all, we will move to the grooves and activate output groove as contour, because we need the contour now for our slot miller. IMOS will write in contour, it's not macro anymore. It's the most important setting here. Then, in this case, if it is not macro anymore, the infeed in percent will not be active, because the contours we know from the previous online academies, the contours are controlled by IMOS. Therefore, we have here split grooves in single saw cuts and overlap when splitting 1 millimeter. It means if the width of the groove is bigger than the depth of the saw blade, it should be done many times here, many cuts, and to reach those 10 millimeters, the width of the groove, it should be done some more single cuts here, because the thickness of the saw blade is 3.67 millimeter. Therefore, here is this setting, overlap. If we have here activated the contour, we can use also this interesting function, execute insert mode via CAM center active. It should be activated, and in case it is activated, we can use here the inserting mode. There are 3 options. We will start with begin at the start point and generate the program. What is important here also, for this groove, for this groove I have to choose another part. This groove, it's not the milled one, but it's a sawed one. Yeah. Okay, now generate the program and take a look on the result. And what we can see here, it's not the groove anymore. It's not the horizontal groove. It's a milling. It's not the macro. It's a contour, and we can also see the contour here. The contour is generated by IMOS. And we see here the four cuts. If I switch to front, I can see those so to say 4 contours with a different width. It's an overlay of the saw blade with an overlay from 1 millimeter. So I can see now my tool. It's 181, correct. It's a saw as a mill. And now I can see the movements, how it goes with a contour. The next important thing, the next important setting we done was here activate insert mode, and insert mode begins at the start point. Insert mode begins at the start point. It means the insert of the tool into the part. And the start point is here in the corner, almost in the corner of our part. And we can see here the insert point and the last point from our tool. It begins on the start now. And the start is here on the edge. We have other options. Full depth at the starting point. I will save it and generate the program again. And now I can see the changes. Now the mill starts already here, and on the inserting point we have the full depth of our groove here. And here is almost the full depth is reached. The last option here with an insert mode is extension and safety distance. And here will come two values: extension, the extension of contour, and safety distance between the distance between the tool. We can also leave those fields, safety distance and prolong start and prolong end, empty, and generate the program. Then the values will be taken automatically, the default values from the post processor. But we can also put the values here and generate the program. And now we will see how our contour will be extended. Generate the program again. And now we can see here the extensions. Good. It was a milling with a saw, but if we still want to convert it, not to the milling like it is shown here, but to the saw, we can also do it with a switching off the output groove as a contour. And what is important for the users who have Woodward 7, this option, use bottom face for horizontal groove, should be activated, but it's only in case you use Woodward 7. In the previous versions of Woodward, it will be done automatically. So I will delete those values and switch to begins as a start point again and generate the program. Yeah, the insert mode should be also deactivated because we are using now, we don't using the contour anymore. It's also important to generate the program properly. Okay, and now we have again the groove here and the 4 saw cuts. It's not the milling anymore, it's a saw. So we have the option to convert the milling with a saw to the pure saw machining. And this option is here output groove as a contour. In this case, we will write a contour for the milling with a saw. And if it is deactivated, this will be the pure saw machining. In this case, groove sawing horizontal. And for the horizontal grooves milled, we prepared one more example. It's in case if the groove has an, so to say, an angle here, it means the orientation is universal. It's an additional machining principle, mill, slot milling universal. So in this case, the machining with an angle, the universal, will receive this machining principle. Basically, there are the same settings as for the previous ones. So we will simply generate the program and open it. Okay, now we see here our extensions, and here we have angle groove, with a mill. Yeah. And we have our mill here, the milling direction, the overlay, the adjustment, and all the same settings, and the tool as well, the mill. The next topic will be the lock pockets and the faceplates. Basically, the lock pocket and the faceplate and the grooves as well as nothing else are the pockets for IMOS, but it's separate, the separate machinings which you can add also in IMOS, and they have also the separate machining principles. If I will choose it, I can see here cut faceplate. It has the length, the width, the depth. Normally, the depth of the cut faceplate is not big because it's just for the faceplate of the locker, on, for example, for the doors. And the corner radius normally is symmetrically, but it could also be controlled in the conditions. So now switch to the machining principles and move to cut faceplate. As just said, it has an additional machining type, cut faceplate, under the mill, and the same settings which were shown for the horizontal grooves. So let's select the part and generate the program. Yeah, it is here, and it is rectangular pocket. It's normal. And it is a milled pocket in this case. The tool is there, and the depth and the adjustment, the overlay is also, it also work correct. Another machining is the lock pocket. The lock pocket here has the length 150, the width 27, and the depth 40. It differs. It can be deeper, or it can be can get another sizes. It depends from the lock. So, and the lock pocket has also the machining type lock pocket under the mill. A couple of words about the priority. Despite an separate machining type lock pocket, I would like to advise you to set it to the highest priority as the rectangular pockets. So first we will generate the program with VOP macro, and then we will switch to the cam center contour with a correction. Select the part, create the NC data. So it's rectangular pocket, it is correct here, and it is the milling with this tool. All the options we have seen before. The difference is only here. It's an separate machining type. Okay, now switch to the output of the pockets, which comes center contour train 1. And as you can see here, and as it was said on the previous online academy, we don't, the feed depth will not be active here with the tap function, because we are working now with a contour, the cam center contour 1. I will remember, in this case, it is not the VOP macro anymore, but the contour which is controlled and calculated by IMOS. So the feed depth is not active anymore. We will use the infeed via cam center. Here's the next. And of course we need the clean out, because it's a lock pocket and it's not through. So let's simply generate the program with output of the pocket cam center contour and the clean out. And now we see the difference here. It's not the pocket anymore, but the milling because of the contour. And we can see also the contour here. And now we see two. So the first contour, the inner contour, will clean out because we activate the clean out here. And the second contour will make the fine here. We'll make it fine here. The first one is cleaning out, and the second contour if you will deactivate clean out in the woodwork, will be written only this contour, because the clean out is deactivated. Good, but what we can see here, the start point and the end point are the same, and it might happen we would, for the better quality of our machining on the part, we will have the overlay here between the start and the end point on the contour, especially here, because here is a visible part, and that's what is inside will be simply cleaned out. Therefore, we have the following settings, which calls the overlap. So we can put here the value for the overlap, for example, the 30 millimeters, and generate the program again. And let's see the changes. Okay. If I will select this contour, and this is my start point, and now you see the end point is unequal to the start point, and this distance is 30 millimeters overlay, and here as well. That's the start point and the end point, and this is overlay 30 millimeters. There is another option here, rotor path overlay. It's, so to say, to explain it easier, it's an overlay of the tool. If we would like to clean out it more precise. So let's make here the overlay of the tool, for example, 10 or even 4. And now you can see here we have one path more here. Yeah? And it depends on the value. We can add one more path if we will change the value for the rotor path overlay here. Now it will be cleaned out with those two paths, with those two contours. Let's take a look. And the overlay. Very well. So if you want to overlap the contour, you have to use the function overlap in the millimeter. And if you want the better clean out and to control it, you have to use a rotor path overlay. It's, so to say, the overlay of the path of the tools of the mill. And also, as it was explained on the previous online academy, we can use here the function lead in and lead out. It was already shown, so we will insert here again the lead in and lead out factor 2, and now the diameter of the tool will be multiplied to the tool, so we will have the smooth lead in and lead out here and not damage our part. And also we would like to extend our contour that it starts somewhere above the part and not directly here. Therefore we have the lead in value in Z. I put, it's a fixed value, it's not the factor. I put 30, and let's generate the program and take a look. Yeah, 30 is not enough, but we got it. Okay, what we see here now, the first is lead in and lead out. It starts not directly here on the contour, and of course it is important only for this contour because it will be visible and everything which is inside will be cleaned out. That's why this lead in and lead out were not applied to this contour for the cleaning. So it's lead in and lead out, and those distances should be for the inlet and outlet 16 millimeters because the diameter of the tool is 8, Good. And what we can also hear here from top, it's this Z value. The 30 wasn't enough. We can make it, for example, 50. And make the program once again. Okay, and now the milling starts here and it is out of our lock pocket. So if I will switch our tool here, so I can see clearly it starts here. Okay, let's control it. Now in this moment, the tool, the mill, already reached the maximum depth of the pocket. And if I will switch to the front, I can see it is directly on the contour, but I would like to have here the safety distance between the tool when it is already with a full depth and the contour. Therefore, we have here the value milling depth distance to the contour. Let it be 5 millimeters. And okay, now I have to catch the moment when the mill has a full depth. And now from the front, I will check where the mill is. Okay, now we have this distance here. These are the 5 millimeters between the tool when it is already reached the full depth and the contour. The next and the last interesting thing here is in feed with come center, because the feed depth is not working anymore. In this machine you can also see that it's not applicable anymore, because now IMOS is responsible for this contour because it's come center contour train. In feed via come center. In this field, the linear divisions should be written. For example, if you want to divide the depth of your pocket into 2 milling contours, you have to write 1 to 1 and save it. Generate the program. Okay, and now you have here, instead of 2 millings, the clean out and the contour, you have 4 of them. It's because we implemented the linear division 1 to 1. It means first will be done one contour and then until the half of the depth of the pocket and then the whole pocket. Sometimes it could be also uncomfortable to work here with a fixed linear division. Therefore, you can use our tab function and set the tab function. For example, like this. It's again the system variable for the machining depth, the depth of this pocket. And if the depth is below 22 millimeters, the linear division should be 1 to 0. And if the depth of the pocket is below 44, it should be 1 to 1. And if it is deeper than 44, it should be 1 to 1 to 1. It means in this case, the whole depth of the pocket, the whole depth here, will be reached with 2 millings, with a 2 in 2 steps, with 2 milling contours. And if it is deeper than 44, divided to 3 steps. You can also generate now and take a look. Okay, yeah. Our pocket has a depth of 40 millimeters. Here it means 40 is less than 44 because of the tap function, and it should be done 1 to 1. 1 to 1 means the whole depth will be arrived into the 2 steps, and we have 2 contours, one contour for the clean out here and one contour for the milling of the finishing the contour. And we have now every milling 2 times, but with a different depth here. This one milling will now go only until the half of the depth because of 1 to 1, and this contour is going to the whole depth here. So it's everything for today. We're finishing our online academy. It's a part 2. In the part 3 we will learn also not the horizontal grooves but the vertical grooves, and not only the milled but also the saw principles.